Hello, student, and welcome for the Turbo Machinery lecture series. Today we'll discuss the simple impulse turbine. Yesterday we have seen the difference between reaction turbine and impulse turbine. Also, we seen how the turbines are going, steam turbines are work. Then we have also seen the basic classification in between of steam turbine, different laws, and the basic application. Now today we will discuss. Yesterday we have seen the difference between impulse and reaction. In impulse, initially the steam came from the nozzle and which is further travels to the moving blade. But in case of reaction, the steam came passes through a fixed blade first and then a moving blade. So at initially the pressure inside the steam in impulse turbine is high. But when it passes through the moving blade, the pressure is get constant. And the same time, when the that velocity is get increased when it travels from nozzle and decrease when it travels to or passes over the moving blade. But in reaction, the pressure is at initial is very high. When it when steam is passes through the fixed blade, it reduces. When again it passes through the moving blade, again it get reduced. So it never be a constant anywhere. So pressure is continuously, gradually going to be reduced, which each step. In case of velocity, when stream is passes through the fixed blade, the velocity get increased. When it passes through the moving blade, the velocity get suddenly uh, reduced. When it passes through the fixed, it again increase and through moving blades, it get again decrease. Okay, so that is the difference you should have to remember in between impulse turbine and reaction turbine. Okay, now with respect to impulse turbine, we can say work with the impulse principle where the kinetic energy of jet steam is used to expert a force on the set of moving plates. Uh, you can see at the top portion, it's an impulse reaction turbine, which is nothing but it's a combination of both. Okay, so in the combination, we can utilize both. Pressure drop is affected partly in a nozzle and partly in a moving bed, whereas it is designed in such a manner that the expansion of the steam is takes place in between them. The high velocity jet from nozzle produce an impulse on the moving blade and jet coming out from slight higher velocity from the moving blade produce an reaction. In this type of turbine, there is application of principle, namely impulse and reaction, both can be utilized. Now there are some basically the process, or you can say the working is mixing combination of both, that is impulse as well as reaction. There are several rows which are moving blades fixed to the shaft with equal number of fixed blades attached with the casing. Shaft are always carries moving blade and the casing is always carries fixed blade. Okay, so based on that number of जितने भी fixed blades हैं, based on that the nozzles are to be designed. Okay, now the steam is admitted initially from the steam is admitted initially from nozzle to the fixed blade, nozzle to the fixed blade. Okay, and after that it passes to the moving blade. Now it comes with the nozzle to the fixed blade. If you see the velocity or pressure at initial stage, pressure is very, very, very high. Okay, and it get dropped in the first step when it passes to the fixed blade. Again, it goes down when it passes to the moving blade. Again, it goes down when it passes to the next combination of fixed and moving blade. Okay, it continues till the last mm, combination of fixed and moving blade. Okay, now when the steam is passing through each set of blades, okay, so in that condition, when it travels from fixed blade, the velocity is get increased, and when it passes over the moving blade, the velocity of the steam is transferred to the moving blade, so that the moving blade is going to be rotate in the direction where जो भी steam का direction रहेगा उस direction में moving blades rotation करना चालू कर देंगे. So in other, we can say the conversion of kinetic energy of an steam into the mechanical energy of an plate. Okay. So in this manner, this turbine is work. The example of this type of turbine is Parsons reaction turbine. Okay. Now look at here. The initial stage, the nozzle is converted the high pressure into the kinetic energy. The sets of blade as well as moving blade are to be placed in the sequential manner so that the steam can be passed without dropping its pressure and velocity. The angles are plays a very important role in this case. Now compounding. So it is very important to why the compounding or purpose of compounding. In a high pressure or you can say pressure up to 100 to 140 bar, the high temperature steam is used in a power plant to increase the thermal efficiency and to reduce the size of plant. If the entire pressure drop from boiler pressure to the condenser pressure is carried out in a single stage, then the velocity of the steam enters into the turbine will be extremely high, as the velocity is directly proportional to the turbine and which can be produced the rotation speed up to 30,000 rpm, which is too much high for practical usage of this speed. So hence we need to add reduction gears in between turbine and generator. Okay. So after that the generator will be rotate at a particular speed so that it can convert the mechanical movement of an shaft into the electrical energy. Also, there is a damage of structural failure of the plates due to excessive centrifugal stresses. The velocity of steam at the exit of the turbine is too high. This will give rise to considerable losses in kinetic energy, which is around 10% to the 12%, which reduces the efficiency of overall unit. It is therefore necessary to incorporate some improvements in the simple turbine, achieve high performance, and this can be done by making using of multiple system of rotors in series, which is normally keyed commonly on a common shaft, so that the either steam pressure or you can say jet velocity is absorbed in stages as it flows over the rotor blades. They will leaving losses also be very less. This process is called as a compounding of the steam turbine. The rotor speed can be reduced with the help of three methods. First, velocity compounding. Second, pressure compounding, and third one is a combination of velocity and pressure compounding. Now it is very important, student, please note that this question is generally asked why the compounding system is necessary in steam turbine. Okay, so theoretical theory will be asked normally for 4 marks, and the explanation about the velocity, pressure, and velocity pressure compounding is generally asked for 8 marks. Okay, so we can prepare accordingly. Now let's see velocity compounding. Okay, in the right side you can see a simple animation how the steams flow, how the velocity steam passes through the moving blade, fixed blade. Okay, encasing all the systems has been uh, you can uh, visualize properly. So in a longitudinal section and variation of speed, velocity, and specific volume of the stream of the steam for the velocity compounding, velocity compounded of the turbine, as shown in right side of the figure. It consists of set of nozzles and 4 rows of moving blades which are fixed to the shaft, and the row of fixed blade which are attached to the casing as shown in figure. The steam is the steam is expanded from the boiler pressure to the condenser pressure in the nozzle. There is a drop, there is a sudden drop in in pressure and increase in velocity. You can see uh, in pressure velocity diagram. There is no drop of pressure either. It travels from moving blade or fixed blade. The pressure remains constant in the blade. You can see it at the bottom. Just a minute, I will highlight that region. Okay. So in this region, you can see when at initially the pressure is dropped down when the steam is enters inside the first blade set. Okay. After that, the pressure is kept constant. After that, the pressure is kept constant. Due to decrease in pressure in the nozzle, the steam acquires a very high velocity. And this high velocity steam first enters in the row of moving blade. आप देख रहे हैं उसके where some portion of velocity is going to be absorbed. It then enters to the first row of the fixed blade. The function of fixed blade is only to guide the steam coming from the first moving blade row to the next moving blade row. There is no change in velocity as the steam passes over the fixed blade. The steam then passes on the second row of moving blade where the velocity is further reduced. You can see the velocity diagram. Then the steam passes to the second row of moving blade where the velocity is further reduced. Thus, the fall in velocity occurs every time when the steam passes over the row of moving blade. The steam leaves the turbine with very low velocity. Thus, a drop in velocity is arranged in many small drops where the several rows of moving blades. It is called as the velocity compound of the turbine. The specific volume of the steam remains constant during the flow. Hence, the blade height is the same in all rows. This method is called as a This method of compounding is used in Curtis turbine. Okay, so generally it is asked in examination. You should know the basic diagram. You can draw this diagram also, and based on that, uh, this velocity compounding we are looking for impulse turbine. Okay, and such kind of turbine which possesses velocity compounding, that is called as a Curtis turbine. Okay. Uh, Here the three row velocity compounding impulse turbine has been shown. The steam is entering from this side. Steam is entering from this side. It passes to the work state of moving blade, then guiding blade, then moving blade, then guiding blade, then moving blade, and it leaves the turbine. I hope you will understand the process, how the steam increases, how the pressure and velocity get maintained. Here's the velocity of each time it reduces with a particular set. Okay, when steam is in contact with the moving blade, then and then only mass velocity gate. Okay, now what are the different advantages? Okay, few number of stages are required, and therefore the initial investment is very low. Also, the space required for overall construction is also low. The pressure in a housing is considerably lower, meaning that the cost, total cost, and the manufacturing cost of this kind of compounding turbine is very less. So, as we can use less thickened uh, casings for the turbine. What are the limitations? The friction losses are too much because of the high velocity of the steam. Maximum efficiency and the efficiency range decreases the increasing number of stages. The power developed in each successive blade rolls decreases with increasing number of rolls, and all the stages are not used with equal economy because each and every stage the velocity is getting dropped. So the efficiency of each stage are different, and the overall efficiency will be dependent on that. Now next what is pressure compounding. Okay. Similarly, if we look at the difference between the velocity compounding and pressure compounding, in velocity compounding we want to use impulse turbine. In pressure compounding, we are using again the impulse turbine. Both compoundings we are looking for impulse turbine. Okay, look at here in the in the segment of velocity. In when it travels initially, the pressure is at fixed condition. Okay, it is going to drop when it passes through the moving blades, nozzles. Then when it travels from moving blade, it is constant. Again, it get dropped. Again, it get dropped. Then again, it is constant. Drop, constant. Okay. So in previous case, it is directly dropped in one set and constant for other portion. Okay. But in this case, it is going modified. Now you can look the first three set and second set. There are two sets which is need to be considered. So in first stage, the pressure is dropped, then it is constant, and in a single stage, it is get dropped. So initially, it is dropped in a reaction जैसे रिएक्शन टरबाइन में ड्रॉप होता है वैसे यहाँ पे ड्रॉप हुआ था उसके बाद वेलोसिटी कंपाउंड में जैसे हुआ था प्रेशर कांस्टेंट रहा था फ्लोट तो सेकंड स्टेप में वो वैसे कांस्टेंट रहता है अब यहाँ पे देखो वेलोसिटी इज इंक्रीज व्हेन इट passes through the fixed plate reduces when it passes the moving and it continues till when it exits. So you can look the diagram which is shown the longitudinal section and variation of pressure, velocity, and specific volume of the steam. for pressure compounding turbine. It consists of one row of fixed blade at the entry of each row of moving blade. The total pressure drop of the steam goes down, and which is with the help of single nozzle, but it is divided into different rows of the fixed blade, which is worked as a nozzle. The steam from the boiler enters at the first ring of the nozzle, where its pressure is partially reduced and its velocity get increased. It is then passes over to the mix of fixed moving blades ring, where nearly all the velocities get absorbed. The exhaust from first moving blade ring enters in the next nozzle of ring. It again the pressure get dropped and velocity get increased. Okay, and further it passes over the moving blade. This process is repeated till the steam leaves at condensation pressure. The steam is expanded partially in each ring of nozzle and pressure remains constant over the each ring of moving blade. The velocity of steam enters in the moving blade is considerably reduced as the pressure is reduced in each stage. As the total pressure drop is split into the series of pressure drops across the several stages, hence the turbine is called as a pressure compounding impulse turbine. As the pressure of the steam gradually decreases, the specific volume of the steam gradually increases. Hence the blade height has to be increased towards the low pressure side. This method of compounding is used in reactive and Joule turbine. This is most efficient type of impulse turbine because the ratio of blade and velocity to the steam velocity is remains constant, but it is expensive as the number of stages are very large as compared to the previous one. Now, next one is the pressure velocity combined combination, which is shown. Now, it is interesting part when you observe the pressure velocity diagram. Okay, so when it passes through the nozzle, the pressure is get dropped. But still, the pressure is constant. Now, look at here. The pressure is constant for first stage. Then it get increased. Okay, then it get increased by adding the other one more nozzle. Adding this one more nozzle. So the pressure get increased and further it is utilized for second stage. So as so on, the number of stages you can utilize. So this type of turbine is combination of pressure and velocity compoundings, which is shown in figure. The arrangement shows is only for two rotors, one of each two rows of moving blades are to be attached. The total drop in the steam pressure is carried out in two stages, and the velocity obtained in each stage is also compounded, which you can see in the figure. In the first set of nozzle, there is some decrease in pressure, which goes some kinetic energy to the steam, and there is no drop in pressure in the two rows of moving blades and the first row of fixed blade. In the second set of nozzle, our remaining pressure drop takes place and the velocity get increased. The velocity drop takes place in the moving blade as in the second rotor as it transfers its kinetic energy to the blade so that the blades are start to be rotate. The blade height in the second stage must be higher than that of the first stage as the pressure is reduced and so the specific volume is get increased. As it results in a bigger pressure drop in each stage, it requires less number of stages and uh, is more compact turbine as compared to the previous one. And It is rarely used now because it has very low efficiency. Okay, you can see the combination properly. Now, next one, the most important task to understand the velocity diagram for impulse design. Just a minute. Okay, so we know that the steam is travel with nozzle and it passes over the curved shape of a blade. Okay, now it is quite similar to that of the impulse turbine, which we have seen water impulse turbine. Okay, it is quite similar. The nomenclature which we are using over here, also similar nomenclature which we was used in a impulse water turbine. Okay, so we can refer the same velocity diagram. If you can see properly, these are the nomenclature. Small use the circumferential, you can say tangential linear velocity of the blade. This one is the absolute velocity of the steam at inlet. Now, rather than uh, water, we can say steam now. Okay. Then A1, that is absolute velocity. V2 or VA2 is absolute velocity, which is exhausting or outlet of the moving blade. VW1, that is World's velocity at inlet, which is V1 in cos of alpha 1. V2 is the velocity, that is whirling velocity at exit, that is V8 in cos of alpha 2. Vf is the flow velocity of sound at inlet of moving blade, that is Va1 sine of alpha. This relation or can this equation we can find out with the help of the velocity diagram. Okay, so m dot we can consider as a mass of steam, is the diameter of drum, s is the height of blade, alpha is the angle, which is absolute velocity of steam in inlet and makes an contact with the plane of moving blade or nozzle angle, or you can say outlet angle of the fixed blade. Alpha 2 is the angle which the absolute velocity is out at outmax with the plane of moving blade, or you can say inlet angle of the fixed blade. Beta 1 is the inlet angle with moving blade, and beta is the exit angle with the moving blade. Now we can see the basic G level impulse turbine. सब लोग ध्यान से सुनो इस इससे न्यूमेरिकल पूछे जाएंगे इन एग्जामिनेशन so properly आप इसको understand करो which is quite similar to the impulse turbine और hydraulic impulse turbine उसके जैसे ही है आपको यहाँ पे याद रखना है वहाँ पे हमने पानी यूज किया था यहाँ पे हम लोग स्टीम यूज कर रहे हैं okay now you can see velocity diagram for uh, impulse turbine. Okay, pressure equivalent. Both velocity triangles has been shown over here for single stage of impulse turbine. Okay, so we know the process how the steam sorry, how the steam get in, is the steam get leaves to the moving blade. Okay, so based on that, the various angles where come various velocities have been generated. You can see the first part, the triangle is for inlet and the triangle is for outlet. Okay, and it's quite very much similar with the impulse turbine. Okay, hydraulic impulse turbine. So we can directly move forward. Okay, now look at here. In examination, we are normally drawn in a steam turbine that is both combination of both inlet and exhaust velocity diagram in one velocity diagram, that is called as a combined velocity diagram. Okay. To remember this, it is quite very simple. You can start with alpha 2, alpha 1, beta 2, beta 1. VR2, VR, VA2, VR2. Then vice versa. VA1 and VR1. In initial at the last, that is a VF2 and VF1. Now the whirling velocities at initial alpha 2 तक जाएगी VW2 और जो remaining रहेगी VW1. And in between alpha 1, alpha 2, alpha in between these 2 point A to point B, okay, it is tangential velocity. Okay, I hope you will this trick will be you will remember to draw this combined diagram. Now, uh, what is the blade velocity coefficient? The blade velocity when for the blades with a smooth surface, it can be assumed that frictionless, or you can say having a zero friction. But in actual practice, it is not possible. So there is a little certain loss of velocity during the flow of steam passes over the blades. Okay, and then loss is take consider. We need to consider this loss, which we are introducing in the factors such as the blade velocity coefficient K. Okay, and that can be found out with the ratio of VR2 divided by VR1. So relative velocity at exit divided by relative velocity at inlet, so that we can find out the percent ratio of the velocity drop. Now blade speed ratio, the ratio of blade velocity to the absolute velocity, that is u divided by v1. Now carryover coefficient. When the steam passes over the one stage to the next stage, the kinetic energy of the steam available at the succeed row of moving blade is to be utilized and is less than at the exit of the preceding row. As a part of energy, it losses in some energy is losses in the passage before entering to the nozzle. This fraction of kinetic energy corresponds to V2, which will available for utilization in nozzle for the succeeding stage. It is called as a carry-over coefficient. Okay, और एक चीज याद रखना 100% कोई भी स्ट्रीम कैरी ओवर नहीं होती because there is a gap. In that gap, the steam is lost some of the portion. Okay, so this carryover coefficient we are always consider for 90% to 95%, that kinetic energy which is considered of the exhausting the first stage is dropped down to the 90% to 95%. Okay, so as the number of set of nozzles are getting increased, the conversion will be over there. Now, basic calculations for power, work power, and different efficiencies. As we know, we are using Newton's second law, that is tangential force is proportional to the rate of change of momentum of the steam as it flows over to the plate surface. That is, the tangential force is equal to mass per second into the change in velocity of the ball. That is m into Vw1 plus minus Vw2. Okay, so the direction is depending upon plus minus sign is depending upon the direction. Okay, and multiply by speed, where m is the mass of flow of the steam kg per second. If the Vwt is opposite in direction of the tangential velocity, then force is equal to m Vw1 minus Vw2 into n. That is Vw1 minus Vw2 into n. If the Vw2 is in the same direction of tangential velocity, then F is equal to m VW2 minus VW1 minus VW2 into N. Now work done by the steam over the plates. So that is a force into displacement. Work done is nothing but a force into displacement. So work done in the steam turbine per second, the force is equal to m VW1 plus VW2, and the displacement is u. Okay, so equation is W into m into VW1 plus VW2 into tangential velocity. The power developed in the turbine the- is equal to m, that is work done divided by 1000. So you can get the power developed by turbine in kilowatt. Now axial thrust. The vertical component of the absolute velocity provides an axial thrust, which we need to consider during the calculation, which is over the periphery of the uh, on the bearing, and it is quite undesirable. It can create a vibration, then choking. So we need to balance and provide a particular provision for thrust bearing, as it makes the makeup of this kind of. The axial thrust on the wheel is obtained due to the difference between the velocities of the flow at entrance and the outlet of the blade. So axial thrust is equal to mass into change in velocity of the flow. Mass is m. Change in velocity of flow is Vf1 minus Vf2 into n. Now tangential force on blade Fu is equal to mass into Vw1 minus Vw2, or you can say mass into the difference between Vw, the work done per time, or you can say power developed due to the tangential force is equal to m into u into Vw1 minus Vw. The blade efficiency, or you can say diagram efficiency or utilization factor is equal to, that is efficiency, blade efficiency is equal to work done divided by kinetic energy to be supplied. That is m u Vw1 minus Vw2 divided by m into V1 square divided by 2. So the efficiency of the blade is equal to 2u Vw1 minus Vw2 divided by V1 square. All are requested kindly note down these important formulas before starting the calculation or start solving the problems. Now, the stage efficiency. The stage efficiency is the work done by the rotor divided by isotropic enthalpy drop. So, the work done by rotor is, we have already seen, that is m u into Vw1 minus Vw2 divided by, now isothermal enthalpy drop, that is m divided by delta H. Okay, so putting all the values we can find out. You can also find out the stage efficiency is equal to blade efficiency into nozzle efficiency. Okay, the energy converted into heat due to the blade friction. The loss of kinetic energy during the flow of steam over the blade is equal to 1 half m, that is mass of steam, into VR1 square minus VR2. The energy lost at the exit is equal to 1 half m VR2 bracket square. Now blade efficiency, again we have already seen this one. Okay, now you can find out the W max, which is nothing but 2u, sorry, 2u square. Okay, that is whole. Now comment of the maximum efficiency, that is maximum blade efficiency, is equal to cos square alpha 1. Okay, as you can see, When the maximum efficiency of the steam that cos alpha is equal to 1 or alpha is equal to 0. For the zero value of alpha, the axial flow compound would be 0. But it is essential to have an axial flow compound to allow the steam to reach the blade and to clean the blade on the living. As the alpha increases, the work done on the blade gets reduced. At the same time, the surface area of the blade reduces. Thus, there is a less friction losses. Where this conflict required, the blade angle is in between 15 degree to 30 degree. Now, variation in blade efficiency and work done with the blade efficiency ratio, that is U divided by V1. The maximum, as you see, the maximum work done, that is 2U square. Okay, when the blade speed at initially, let us consider as 0, that is P is equal to 0, no work is done as the distance traveled by the nozzle is 0, blade is 0. However, the torque of blade is maximum. When P is equal to cos alpha 1 divided by 2, then the maximum blade efficiency is given by cos square alpha 1 and the maximum work done is 2U square. When the P is equal to 1, the work done is 0 as the torque acting on the blade is 0. As both blades and steams are moving at the same velocity, however, the distance traveled by the blade is a maximum. Now, okay, you can refer to the first problem. Okay, uh, in the first problem, it is mentioned. Uh, okay, rather than this, I can take the problem on impulse turbine in a classroom. Okay, so you need to understand the basic theory of the impulse turbine with the different compoundings so that you can utilize the proper conversion of and pressure and velocity to get the maximum out output. Okay, so I will stop today to stop this lecture over here. We will see problem in a class. Thank you very much. In description, the attendance link has been given to you. Kindly fill the attendance. Okay, thank you very much.